I hope.
Yes, it's fine.
Okay, so thank you very much. So this is, I'll switch gears a little bit to talk about some recent and not so recent results from Lattice QCD in OpenCharm. Maybe I can just apologize a little bit just in advance. My network connection has not been very strong this morning, so I hope it will hold out for the duration of the talk, but I apologize if there are any issues. Okay, so this is work on behalf of as part of the Hadron Spectrum collaboration. And of course, I don't need to tell this audience that the OpenCharm sector is, of course, a very rich and fruitful playground for us with many puzzles and challenges to address and to think about and to help us to explore the dynamics of QCD. So what I'll talk about here are some older calculations of the spectrum of D and DS mesons, including hybrid meson predictions. And you saw a little bit, I think, in Nora's talk yesterday, where she talked about hybrid mesons as they appear and are predicted in charmonium and bottomonium sector, and this will be very analogous in the heavy light sector or the OpenCharm sector. And then I'll spend a little bit of time talking about more recent work on D0 star and DS0 star in D pi and dk scattering respectively, which is really investigating the puzzling inversion of the mass hierarchy between these two states as observed at experiment, and asking what Lattice can say about that. So I'll show you some results from recent work on those topics. So of course, this is a very active field. Ours is not the only work, and in fact, there has been a long history of Lattice QCD studies of d pi and dk scattering already, some of which are listed here for reference. It's probably not a complete list, so I apologize in advance if I have missed out some work. And of course, outside of lattice calculations, there have also been very significant work by others, many of whom are in the audience as well today. Okay, so for the lattice calculations, maybe just to focus a little bit on D0 star at the moment. So I'll talk about this in d pi scattering, elastic scattering, just to highlight that, of course, there's been previous work, as I said, already quite some time ago. And in this very nice paper by Daniel Moeller and collaborators, they found a resonance close to the PDG average. So what our objective in the HandSpec collaboration was to map out the energy dependence in these scattering states, determining the pole positions to understand the mass ordering, as I already discussed very briefly. And I'll say a little bit as well, you'll see some results about how we can use the lattice calculation to understand something about the light quark mass dependence in these two states. So I'll be drawing on results that have appeared in various papers, some going back quite a while now to 2016 for the spectroscopy and hybrid mesons, and some more recent work on d pi scattering and dk scattering, and the references are given to you here. So in very quick summary from the lattice calculation that we've been doing, these are based on anisotropic lattices where the spatial and temporal lattice spacings are different. In particular, the temporal lattice spacing is much finer, so it gives you a lot of resolution in the temporal direction and helps as you extract and measure energies in that direction. So some of the parameters are given here with 2+1 flavors of fermions. These are Wilson-Clover fermions. And as you see on the table, we have 2 pion masses corresponding to 239 MeV and 391 MeV on volumes where m pi L is between 4 and 6. Just to highlight that one of the strengths of these calculations is the very large operator bases which we're able to construct. That includes fermion bilinears, so QQ bar type operators, but also meson-meson operators, which of course play a fundamental role in work, for example, in the dk or the d pi scattering. Maybe also just to highlight that there's a significant amount of effort that goes on sort of under the hood, if you like, in constructing optimized operators so that the energies that are extracted are as precise as possible. And there are lots of details, of course, in many papers. The two papers that I alluded to above in d pi and dk are given in more detail here, the references for the JHEP references. And I'd just like to point out as well that this is really work was driven by a number of graduate students in our groups. So in particular, Nicholas Lang, Luke Gare, and Gavin Chung. So thanks to them for this hard work. For the lattice aficionados in the audience, here are some sanity checks. So this is an anisotropic lattice. We can map out the dispersion relations in both for the D mesons and the DS mesons. So on the right-hand side on the plot, you see those dispersion relations. These are for relativistic charm quarks on these anisotropic lattices. You see that these are very consistent. The anisotropy, which is extracted from the slope of the dispersion relation, is consistent for the D and the DS meson, and also at the different volumes that we have at our disposal. So all of that is mapped out on those dispersion relations. And remember, again, just to say that the input parameters in these calculations, of course, are the quark masses. So for example, the charm quark mass and the bare anisotropy, and these are tuned once, for example, at the in charmonium. And so when you see these relativistic dispersion relations in the heavy light sector, it gives you some confidence that everything is working very well. Okay, so very briefly, the idea here is to compute correlation functions. We do this using distillation, which is an approach to quark propagation that has lots of very nice properties and underpins a lot of the spectroscopy that we're able to do. The correlation functions, of course, we make many of these correlation functions, as I've already said, including a large basis of operators with structures which are fermion bilinears, but also more complicated structures, these meson-meson type operators, which I've sketched for you in these two expressions here. From this large basis of operators, using a variational analysis, we essentially solve a generalized eigenvector problem. And then from that, you can extract the energies from the lattice calculation as fits to sums of exponentials. So on the right-hand side, you just see, and this is just as an illustration, some of the energy levels that can be extracted. So the energy levels that are extracted from the lattice calculation, this is in dk, just as an example. At zero momentum in a particular lattice irrep, so the A1 irrep, and the points that you see for this particular volume was 32 cubed spatial volume, and you see a series of points. So these are the energy levels extracted in this particular irreducible representation for this particular state. But the underlying, or the technology underneath this, of course, is as described on the left-hand side of this slide. So maybe just to point out again, we can extract, typically in any of these irreducible representations, we can extract a large number of these energy levels, and those all feed into this analysis, as I'll discuss. Of course, here's a more complicated and messier picture, but just to give you a sense of the, as I said, the information that's fed into these sorts of analyses, including from many lattice irreps, many momentum combinations. This is for dk. And again, you see the points, which are the information that's measured or calculated in this lattice calculation, just as an illustration of the amount of information that's fed into the calculation. So what do we do with these energy levels that we can extract, as I've discussed just previously? Well, again, I'm sure you're all very familiar at this stage for how this works in the lattice calculation. So we know for some time now how to take these energy levels extracted in a finite volume and translate them to infinite volume amplitudes and to extract the scattering information from that step. So this is from the Lucia method, and of course extensions, many extensions which have been made to that method that allow us to extract that scattering information, essentially a T matrix of infinite volume, from those finite volume energy levels that we've measured. So in this case, I'll be talking about elastic scattering. Essentially, maybe just to point out just that this cartoon down here, of course, the more information you have from finite volume energy levels, so the more energy levels you have, what the Lucia method allows you to do is to map from those finite volume energy levels to some, for example, phase information And of course, the more information that you have, the more energy levels that you have, and the more precisely those are determined, the better you can map out that energy dependence. And that, of course, is an important part of this analysis. The T matrix, of course, essentially is undetermined by this Lucier condition, or at least the parametric form of the T matrix. But there are some constraints that we can use, and typically then a range of parameterizations of the T matrix are considered, including, for example, K matrix, effective range, etc. And those, as you'll see in later results, form or can be used to at least estimate some uncertainties or in the parameters that are extracted. This is, we then can analytically continue in the complex plane and look for poles. So those are the essential steps. Let me really, in some sense, take almost a step backwards now and just consider the spectrum of D and ds mesons formed from single hadron states, so fermion bilinear. The operators are just fermion bilinears here. I'm not considering any scattering states, but the operator basis does include hybrid-like operators to allow us to pull out or to identify those hybrid meson states. So this is rather old work, but just to set the scene, this is the spectrum for the D meson of states, which we were able to determine using these single hadron operators only. This was done at two different light quark masses, as I mentioned earlier, and you can see those side by side for each of the continuum JP numbers that we reproduce in this calculation. So the height of the boxes, these are all the energy levels which are extracted in the lattice calculation. The height of the boxes represents the statistical uncertainty in that calculation. And although most boxes are green, you see some are highlighted in red, and those are the hybrid-like states, or the states which have overlap onto hybrid operators predominantly. So since this is maybe of interest to people, I've pulled out just the channels where those hybrid mesons were identified in D and in DS. So this is at a relatively heavy pi mass, just one of the pi masses that were considered on the previous slide, the heavier of the two. We've repeated this analysis on the lighter pi mass and see essentially a similar pattern of states in both D and DS for the lighter pi mass. And just to make some connection also to charmonium, to quarkonia, charm and bottom quarks, CC bar and BB bar. Again, this is the similar prediction of hybrid mesons in those sectors from similar lattice calculations. And you see here, again, a similar pattern of hybrid supermultiplet, the lightest hybrid supermultiplet distributed around these, in this case, JPC assignments highlighted as the red states here. So we see a very similar pattern and also scale for these hybrids across all sectors from light quark all the way through charm, open charm, and on to charmonium and bottomonium, suggesting some similar physics of play. Okay, so that's what we can do with sort of simple single hadron operators. Of course, what's interesting, and you saw from the previous slides also that many of the states that we're extracting lie above standard K thresholds and so are more correctly treated or should be treated as resonances. So here's some work on d pi scattering and the d0 star. So here for d pi in isospin 1/2, there was quite some time ago now, we did a first study of this system at a heavier pi mass of 391 MeV and found a shallow band state just below threshold. What we find when this calculation is repeated at the lighter pi mass is the pole migrates into the complex plane and ends up at about 77 with a large uncertainty MeV above threshold. So the conclusion here is that there's a D star resonance pole with a mass and a width that are given here at the top right. And maybe note that the mass that we estimate from this calculation is below the reported experimental value, despite the fact that these are still unphysically so unphysically heavy, if you know what I mean, like quarks. Also, just to note, there's a strong coupling of the poles to the d pi channel in both cases, where I mean both pion masses. And you can see how the amplitudes evolve. It's a little bit, so I apologize, the labels are a little bit small, but the sort of teal colored curve is the heavier pion mass, and the lighter pion mass is illustrated in red here on the left-hand side. And similarly on the right-hand side, you can see the pole positions and the change in the pole positions as you move from the heavier pion mass to the light pion mass. So maybe this is a good point, a good time just to emphasize that one of the strengths, I think, in these lattice calculations is the fact that the pion mass is a parameter which we control, and so we can learn quite a lot by repeating these calculations at these different pion masses and understanding the behavior and the dependence on the pion mass in these scattering parameters. So it gives a very nice window into this behavior from a lattice calculation. Let me turn then to decay scattering. So here, of course, the state that we're interested in, at least in this snapshot that I'm going to present to you, is the DS0 star. So here again, just a short summary of the work that was done. And I should say that there's a significant amount of technical information and indeed other work that I'm not discussing here just in the interest of time, but which are all described in detail in the papers that I referenced earlier. So for decay scattering, this is in isospin 0. Again, similar picture, these plots are essentially related to the amplitudes, the squared amplitude. And again, you see side by side the results in S wave and P wave at two different pion masses, 391 and 239 MeV again. So what you notice in this elastic scattering, so this is decay scattering in S and P wave, a very sharp turn on in the S wave at threshold. Again, as labeled here, S wave is the red with the curve, and P wave the green. Underneath you see many points, and these are the energy levels, again going back to the point that I made earlier, the energy levels which feed in through the Lucia method to allow us to extract these amplitudes. And in this case, for example, we have 22 different energy levels at one of the pion masses of the lighter pion mass, and 34 energy levels at the pion mass of 391 MeV. So there's really quite a lot of information that goes into constraining these curves. The bands that you see both reflected in S wave and in the P wave are related to the different parameterizations of the T matrix that I also discussed earlier. And so you see that this can lead to some significant uncertainties in the amplitudes and then in the scattering parameters that are extracted coming from these different parameterizations. So what do we see if we just focus on the S wave poles in decay? So there's a summary on this top picture here. And in red, you see the location for the DS0 star for the lighter of the pion masses that we have in the simulation, and in blue, the DS0 star for the heavier of the pion masses. Also reflected here are the thresholds for decay at both of those pion masses. So you can see how the location of the poles evolves with respect to the thresholds as you change the pion mass. Just to quickly note that we also find a deeply bound state in P wave, but this is not strongly influencing, at least, the scattering at the energies that are considered here. And to sum up then for this decay analysis, there is a bound state pole which is strongly coupled to S wave. And here you see the distance from threshold given here. So delta E for is 25 for the lighter of the pion masses and of the order of 57 for the heavier pion masses. I've also just included the Weinberg, this Z parameter although I know from earlier discussions this morning that there's, there may be better ways of reflecting or thinking about this compositeness, but just for completeness, I've included them here for both of the cases that we considered. Okay, so I can summarize then from these lattice calculations what we can say about the mass hierarchy for D0 star and DS0 star. So what we've tried to do is to map out the energy dependence, as I said, of the scattering amplitudes using lattice calculations. So just to summarize, in isospin 0, so decay scattering, we find an S-wave bound state, which corresponds to the DS0 star. And in isospin 1/2, in d pi scattering, an S-wave bound state or resonance at D0, which corresponds to the D0 star. And on the plot on the right-hand side, what I've presented in the previous slides is summarized. So on the what you see is the location of those poles as a function of the pion mass for both DS and the DS0 star and the D0 star. And you can see how they move as a function of the pion mass, but also that they follow expectations or some natural mass ordering that one would expect. And so the conclusion here is that the puzzling fact or experimental observation that the D0 star is heavier than the DS0 star is actually not reproduced in this study. And there are similar observations or similar results from other calculations too. There are, of course, many questions that remain. We also, in the same study, looked at decay bar scattering, so in exotic flavor combinations, so in isospin 0 and in isospin 1, and see indications of an S-wave, a virtual band state in S-wave. I haven't really talked about that here, but that's an interesting result, which again, we will need some further understanding, I would say. A further investigation of the light quark mass dependence, I think, can be very useful. So you see here how this is evolving as a function of the pion mass, the light quark mass in the simulations. Of course, heading towards even lighter or physical pion masses requires additional computation, and indeed, of course, also the thresholds move and additional thresholds open for lighter pion masses in these lattice calculations. And so this becomes a more complicated analysis, of course. And I've also not really discussed states higher up in energy, where in particular inelastic or 3-hadron scattering effects should be taken into account. So there are many, let's say, open questions or further directions, even just within these analyses that I presented. So let me summarize summarize the summary, if you like. So just to remind you that QCD describes the properties of matter in terms of fundamental variables, and so lattice calculations offer many potential opportunities to understand some of these puzzling states. There has been significant progress in lattice calculations in the last 10 to 15 years. And so hopefully what I've presented here, but also the other work by other collaborations that I referenced at the beginning, gives you an indication of how active this field is. From the HADSPEC collaboration, there's been an extensive analysis both of excited and exotic spectroscopy of single hand rod states, but also, of course, of scattering. And that's been work in progress in the light sector, in this heavy light, including open charm sector, and also in the heavy quark sector. And this is really just a snapshot of activity in this quick talk to give you a flavor of what is ongoing, and also to highlight that there is a significant amount of work ongoing in different quark mass regimes, and that we can learn or connect what we do in one sector to other sectors as well. Of course, varying the pion mass gives a very nice window onto some of the dynamics at play in these scattering states. And of course, including 3-particle thresholds is a new challenge. There are some early results on the light sector in this, but not not anything very extensive to date, but that will come, I think. So thank you very much for your attention.
So thank you very much, Sinead. Perfect timing. So we have some questions. So Miguel Albadalejo, please.
Hi, thank you, Sinead, for your nice talk. Since you make, parameterization of the amplitude, and from there you can extract physical parameters, and you could extract also the scattering length and the radius, the effective range, right? And do you provide that, or that would be very interesting for the talk that we have been having all this morning.
Sure. I mean, so for example, they certainly feed into the values that I gave of that Weinberg parameter. Whether they're actually in the paper or not, I actually don't remember. That's a very good question. Dave Wilson somewhere is I think is here. Dave might remember better than I do whether we actually quote those numbers.
I'm pretty sure they're in the paper.
I think they must be, because
they might not be plotted, and
yeah,
we definitely looked at them. I don't remember exactly. There's definitely something of them in both papers, I would say.
So I think they must be, Miguel, in the papers that I referenced.
Okay.
Yeah. Sorry, I just don't remember off the top of my head.
Yeah. I mean, I've also read the paper and I don't remember it. So yeah, that's what I was asking. So I will take a look again to them. Thank you.
No problem.
Okay, so there is another...
it's plotted in figure 8 in the D5 paper, for example. There's a K-cut delta plot where you can read off the effective range by eye if you wish.
Okay, thank you.
Super, thanks, Dave.
Okay, there is another question by Sasa Prelopsek.
Well, thanks for a great talk and results. I more have a comment. So we did the first d-pi scattering on the lattice, right? You mentioned it. And then we only did the Bright-Wigner fit at real energies and got the mass for the meson scalar resonance, which is really 2.3 GeV, right? So really close to the strange state. So that was kind of puzzling. But now recently I recalculated, I extracted the pole, the position of the pole, right? And this is really much closer to what you get. So it's at around 2.1 GeV.
Okay.
Yeah, but in 2012, we didn't look for the pole. Somehow that was not so fashionable back then. But now that we look for pole, we see that this is much closer to what you get, so much lower than PDG.
Yeah. Great. Okay, thanks, Sasha. That's really nice to know.
Okay, so Patricia, do you have also a question?
Yes, I think maybe it's a naive question. I don't really understand. So first of all, thanks for this nice talk. Yeah, I didn't understand what you said about the hierarchy problem of the masses, because it seems that you find in agreement with what we expect. So,
well, no, I mean, just that the experiment, the puzzle is that the PDG average places the DS0 star lighter than the D0, which is not what you would expect from some natural ordering.
Yeah, but
we find in both, for both pi masses, that the ordering that you would expect is observed. That is, the D0 star is lighter than the DS0
as
star.
we expect.
Okay.
Yeah. Okay. Just comparing with the PDG, which is the average of. Okay. Now I get it. Thanks.
Okay.
Okay. So Christoph Hanhart, do you also want to add something?
Also from my side, thank you very much for this very nice talk. Well, I have one comment and one question. The comment, first of all, is what is quoted in the PDG is really just referencing what is in the experimental analyses. And since they all did Bright-Wigner fits, they found the same as Sasha did, right? If you do Bright-Wigner fits for near threshold states, you sometimes get scrap. And this is actually what happens here. This is where the 2.3 came from in the first place. In the next PDG issue, as a review of particle physics issue, there will be a footnote, however, for the D0 2300, pointing at the significant incidence that the mass of that state is significantly lower. But we don't yet have enough pole extractions directly from data to really give the pole numbers at this point, but that will hopefully come then in the next printed issue in 24. My question is about the last slide of your results slides. There wasn't a slide number there, I cannot name it better.
Here?
Yeah, here you give an uncertainty to the Z value for your higher pion mass. It's 0.13 plus and minus 6. Is 6, what is this coming from? Is that from the fitting, or is this really already including the uncertainty from the Weinberg criteria in the first place?
It's from the fitting uncertainty.
Okay, thank you very much.
Okay, so myself, I have a question. So I think you have only one lattice spacing, which is temporal.
Yeah.
So when you go to the physical world, how do you compute your uncertainties related to the uncertainties of the lattice spacing?
Okay, so that's it's an excellent question and one that I can't really answer because essentially the short answer is we don't. So these results are at finite lattice spacing, and without, as you quite correctly say, without repeating this calculation at multiple lattice spacings and taking a continuum limit, I can't comment on the impact of discretization uncertainty. So these are results at a finite lattice spacing. So there is an unquantified systematic uncertainty which is related to the lattice spacing at which we do these calculations.
Yes, but because I think in your papers I read somewhere that you have several ways to determine the lattice spacing. One of those is the omega baryon.
Yes.
So if you do a different way, can you get from there somehow an estimate?
So, yeah, it's an excellent question. So I was just about to say essentially the same thing, which is that you can try to estimate what the uncertainty is, and one way, as you quite rightly say, that you might do that is by changing the parameter that you use to set the scale. So we use the omega baryon that's very well determined on the lattice and very well determined in experiment, and so it's a very nice quantity to use to set the scale to determine the lattice spacing that for these ensembles. And so one could change that parameter, but it doesn't give you calculate again the lattice spacing and try to understand what the difference is. But it doesn't really give you I would say a robust estimate of the discretization uncertainties. We did also look at how our results, this is going back quite some time now, to a spectrum calculation. We did also look at how our results depended on one of the coefficient of an improvement term in the action. So it's getting a little bit technical now, but if we were to non-perturbatively improve the fermion action, how that affects the results that we extract, we found at a level of about 40 MeV, which you might assign as a discretization uncertainty to these ensembles. But again, I would caution that that's really not the right way to do it. In some sense, it's an estimate rather than any sort of quantified uncertainty.
Okay, thank you. And I have a short
Sorry
question.
for the long answer.
Yeah. So in your paper, I think you have also studied the decay bar scattering, the exotic state,
yep.
And also the decay bar star exotic one. So but it looks like you get energy levels that are very close to the free energy levels. So can you comment something about that? Like, do you have any difficulties in this exotic sector, or?
Well, I think so. So maybe just to say that so we also looked at D star K, for example, and found a bound state or resonance in D star K. I'm not sure if that's what you were talking about, but but that really needs a couple channel analysis. We also found, as you say, in dk bar, a virtual bound state. But I think there's certainly more work needed there, in particular to understand the threshold effects. So yeah, I'm not sure. Yeah, I mean, I think that's probably, maybe just to say, that's probably for another day, in particular to understand inelastic scattering for some of those states that we looked at in a preliminary, let's say, way.
Okay, thank you. So let's go to the next talk. So the next talk is by Miguel Alvarez.